I'd like to welcome everybody to our first robotics seminar of the year. We do these every month. We'll do these on the first Friday of the month this year at noon in this time slot. If you want to get announcements and aren't already getting it, you can get it by going to the robotics website, robotics.wisc.edu, and signing up for the mailing list. So in general, these talks will be about 45 minutes. To start out with, we're going to be doing the talks online, joined by Zoom. During the talk, we encourage questions. What we're going to try to do today is, if you have a question, put it in the chat. And then when we get to a point that's sort of good for us to take to pause the speaker, we'll stop and either ask you to speak your question, or one of us panelists will relay your question to the speaker. If it's a clarification question that you think is like you really want, like, please stop the speaker right away before he goes on, because we want to clear this thing up. Would like to encourage you to make that clear in the chat, and we'll sort of prioritize making that happen. Okay, so with those mechanics out of the way, I would like to introduce Professor Josiah Hanna, who is now Assistant Professor of Computer Sciences here at the University of Wisconsin-Madison. Josiah has just joined us. We originally invited him to join us 2 years ago after he completed his PhD at the University of Texas at Austin, where he was working on, amongst other things, getting robots to play soccer and be, including being just better athletes and running faster while they were playing soccer. In those 2 years since then, he spent the 2 years in Edinburgh, or I don't know if he was actually in Edinburgh given the pandemic, but working at the University of Edinburgh on related issues on how to apply learning to autonomous systems and robots. And with that, I'd like to look forward to your talk.
All right. Yeah, thanks for the introduction, Mike. It's my pleasure to be here. Thanks for the invite to speak. So learning from interaction is a hallmark of the intelligence that we observe in animals and people. So, as people, we're taking actions all the time. We're observing the outcomes of those actions. And if those outcomes are positive for us, then, we learn to do those actions again in the future. Or if you're a pet owner, if you own a dog, for instance, you might try teaching your dog a trick, and you would give your dog a command. And if your dog does the right action in response to that command, you would reward your dog. And then the dog, as an intelligent creature, is able to realize that, like, hey, I should sit the next time I receive this command. But we can contrast that to how you would get a robot dog, like this Sony Aibo, to sit down. In this case, you would have to exactly specify how the dog should sit down. There's no learning taking place. The dog wouldn't get better at it. If you wanted to change this dog to rolling over, you would have to reprogram exactly how to do that. So arguably, this ability to learn from interaction in order to accomplish goals can lead to very rich behaviors in humans and animals. And so the goal of my research is to give the same capability to computers and robots. Specifically, I want to enable computers and robots to be able to learn how to accomplish their goals through interaction with a task. What this means a bit more concretely is that I want computers and robots to be able to take actions and learn a policy, which tells them from any state of the world, what action should they take in order to achieve their goals. This goal of my research is aligned with the fields of that of reinforcement learning in computer science and artificial intelligence. So there's been a lot of buzz about reinforcement learning in the past decade. So there's been several landmark results for reinforcement learning based on scaling up some very old ideas in the field. For instance, in 2015, Google DeepMind revealed the system that could play Atari video games at superhuman level, just looking at the screen and choosing what control to take. A bit Soon after that, there was the system Alphago, which defeated a human Go player. This was a challenge that was supposed to be, decades in the future before a computer would be able to defeat a human at Go. And then as one more example, here's some simulated robots. This was work that was done by another student at the University of Texas at Austin, where these robots are able to play soccer at a very high level in a simulated environment because they've learned through interaction how to maximize the performance of their various skills. So it's not just like simulations and games, but reinforcement learning has also attracted a lot of interest in industry. So web marketing is one prominent application where reinforcement learning has been successful. So, how do you show ads to get users to click on them? How to control data centers. Google has been very successful at doing this using techniques from reinforcement learning. And as one more example, home thermostat systems can be optimized with reinforcement learning to save energy while maintaining like desired temperatures in a home. So this is very exciting. It's very nice to see these types of applications of reinforcement learning. However, it'd be really nice if we could like take these algorithms and actually deploy them on like physical robots or a lot of other domains which involve sequential decision making. But if you look a bit more closer at these results, you see that reinforcement learning isn't quite yet to where it can be deployed out of the box on a lot of applications. And one of the primary limitations it has is that reinforcement learning algorithms can be very data inefficient. So as these examples here that I'm showing, on this Atari video game, playing, the agent had to try 50 million actions before it was able to, find kind of the optimal policy for taking actions. This result in Go involved the computer playing for weeks against itself, millions and millions of games of Go, just playing against itself to find the right sequences of moves in different states of the game. And as one more example, these simulated robots playing soccer involved 1.5 years of compute time for all of the skill learning that took place there. So this gives rise to the question that I think a lot of people are asking, but it's certainly a question which has guided my research, which is, can reinforcement learning ever be data efficient enough for real world applications? So this is the big question, but a lot of the one of the key capabilities which is going to be required for efficient reinforcement learning is that agents using reinforcement learning have to be able to make accurate predictions about their environment. In reinforcement learning context, there's a lot of things which have to be predicted. And I'm going to talk about a couple of these capabilities, more specific capabilities, in my talk today. The first capability is that an agent needs to be able to predict the effects of its actions. And so today I'm going to talk about improving the ability of a robot to predict what the effects of its actions are in the context of improving simulations so that we can apply reinforcement learning in simulation and what we learn to transfer to reality. So I'm going to be talking about some work today, both that I did during my PhD, but then also some subsequent work which has been happening, building upon that since I finished my PhD. And then in the second part of the talk, I'm going to be talking about a different prediction capability, which is about an agent being able to predict what other agents in its environment are going to do. And I'm going to talk about a particular problem about how it's hard to predict what other agents will do when you can't see certain factors which are influencing their behavior. So that will be the second part of the talk. I think these two problems I'm going to talk about are just like a subset of all the the many interesting, challenging prediction questions, which are very important to solve if we're going to have efficient reinforcement learning. So first, I'm going to talk about how we can improve predicting action effects in the context of sim to real reinforcement learning. Before doing that, however, I'm going to give just a very quick introduction to the reinforcement learning framework, how we formalize these problems, and what this interaction looks like. So reinforcement learning is concerned with an agent interacting with an unknown environment. You can contrast this notion of an unknown environment makes reinforcement learning very broadly applicable. You're not making any sort of assumptions, which you might find in other fields which study sequential decision-making processes. We're just treating the environment as a black box. The only thing that we're specifying is that the agent is able to take actions and that these actions have an effect on the state of the environment. So the agent takes an action, which is passed to the environment. The environment responds by changing its current state and also providing a scalar valued reward signal to the agent. Now, when we say the agent, I'm going to use the notation pi to denote the agent's policy. And a policy is just a function which takes in states and outputs actions. So if you want to think about this in a robotics context, you want to think of the policy as the robot's control software. The actual actuators of the robot, the physical components belong to the environment. The policy is just the control software. In a reinforcement learning, in an environment modeled as a reinforcement learning problem, you can think of interaction as happening as follows. The agent begins in some initial state. It chooses an action and then receives a reward based on that action, taking that action in that state, and then transitions to a new state. And this interaction is going to continue for some fixed number of time steps. And then after that fixed number of time steps, you can think of the interaction ends and maybe the agent goes back to a new initial state, possibly a different initial state, and can attempt the task again. This whole sequence of interaction is called a trajectory, also sometimes called a rollout in a reinforcement learning or robotics context. So the goal in reinforcement learning is we want to find a policy that will maximize the expected sum of rewards per trajectory. So just to show in this definition here, of what a trajectory is, you can see there's a reward at every time step, and what we care about is cumulative reward. So it's not just about kind of taking myopic actions, which are instantly gratifying with high reward, but actually sometimes trading off short-term gains for longer-term gains down the line. And formally, what we would say is that the value of a policy is just equal to the expected discounted future reward, where the discount factor can express a preference for receiving rewards sooner rather than later. So that's reinforcement learning as like a very quick introduction. Because of the generality of the framework, this is why you're able to fit all of these different potential problems. You can model them as reinforcement learning and potentially solve them with reinforcement learning. So while what I'm talking about today is focused on robotics, and then the second part has more to do with autonomous driving, reinforcement learning can be potentially applied to a broad set of problems. So advances for robotic reinforcement learning may improve reinforcement learning for web marketing or for healthcare. So going back to these where reinforcement learning has been successful, one thing to point out is that a lot of these successes have come in environments that can be simulated so that you can generate lots and lots of data for the reinforcement learning algorithm to learn from. So one question would be, why can't we just take, we can't take what was done in the simulated environment and then plug it into some real world environment and what we learn in simulation transfer and work well on the physical robot. So this question, when I started working on this was inspired by my own work that I was doing at UT Austin, working on this RoboCup competition. So this has been going on in my advisor, Peter Stone's lab for a long time. This is working on RoboCup is also now a project. I think it's a great research platform. And so it's something that we're in the midst of starting here at the University of Wisconsin. So if this is something that you think is a cool application, you might be interested in working on, then feel free to contact me about that. But what I wanted to point out here with just showing this video is that you can see very smooth gameplay where the robots are moving. They're moving very smoothly. They're walking quickly, kicking the ball far. And a big part of the success is that their skills have been optimized using reinforcement learning in a simulated environment. And so because of that, they're able to behave much more optimally than if they were just hand programmed. So at the same time that I was doing some work on the simulated environment, I was also working on physical robots playing soccer. And you can see here that the robots move much more, they're less stable, they're walking a lot more jerkily, and they don't kick the ball as far. Also tend to, fall over a lot. There's like a risk of them breaking when this happens. And so we're really just not able to apply the same type of reinforcement learning that's been successful in simulation there. So of course, going back to what I said a couple slides ago, why not just take what's happening in simulation and directly apply it on the real robots? So I think since this is a robotics seminar, I don't think this will be too shocking to a lot of people here, but let's just talk about what happens. So this is an example of what the kind of the naive sim to real approach would be. Here's a robot that's walking in a simulated environment. It's walking, it has this initial walking controller where it moves slowly forward. And in this case, it's dribbling a soccer ball. We can also have an initial hand-coded walking strategy on the physical robot. So that's what this looks like here. This is at the starting point of my research. We can apply reinforcement learning in the simulated environment. That works just fine. We're directly optimizing for what happens in simulation. And so we get a walk which moves much quicker in the simulated environment. However, when you take the same walk, which has been optimized in simulation, and deploy it on the physical robot, inevitably, there's going to be something wrong where the policy that's learned in simulation overfits to the inaccuracies of the simulator, and this causes the policy to fail when it's deployed into the physical world. And so this is very commonly seen in robotics reinforcement learning, and it's called the sim to real reality gap. And because of this reality gap, we can't just hope that applying reinforcement learning in simulation is going to be enough to enable real world reinforcement learning. Let's talk a bit more about what the particular problem is. So this is the kind of the interaction loop which is taking place between a robot and the policy which is controlling the robot. So at every moment in time, the policy receives the state of the world, which is encoded via the robot's sensors, and the policy selects an action, which is commanding the joint angles of the robot, how to move. And this loop induces a distribution over trajectories where the robot starts in some initial state, perhaps just standing still, takes an action, begins to walk, and is rewarded for how fast it's walking forward. And so this happens for a fixed number of time steps. The dynamics of the physical robot are going to induce a certain probability distribution over the trajectories that we see. And so our reinforcement learning algorithm optimizes actions under this distribution of trajectories in order to find like an optimal policy which maximizes reward. If we're doing this learning process in simulation instead of on the physical robot, the distribution of future states is going to depend on the different dynamics the simulator has instead of the dynamics of the real world. And because of this, the policy is actually going to be optimized under the wrong distribution of states. And this is what leads to this reality gap, where the policy is being optimized under the wrong distribution of states, and so it doesn't transfer to the real world. So there's been a paradigm around for a while that can, in principle, address this. So this paradigm is called grounded simulation learning. The idea of grounded simulation learning is that you start with some initial policy that can be executed in the real world. You use this policy to collect some amount of real world data. You then take that data and ground your simulator to try to make it more realistic to better fit so that your simulator is better modeling your real world. You then take this grounded simulator, and that is when you can then apply reinforcement learning directly in the simulated environment. And because you first grounded the simulator, once you take an improved policy out of the training process, you actually expect it to improve performance on the real robot. So the key question then is, how do we accomplish that grounding step? How do we make simulation more realistic? So the first thing we noted is that making simulation more realistic means that we want to make the simulator more realistic from the standpoint of the policy. So that means from the point in time that the policy computes its action, after it's chosen the action, something needs to change between the time that the action goes to the simulator, is executed by the internals of the simulator, and then the next state comes back to the policy. And so what we did in my work, and I think this is what Mike made a reference to in the introduction, was we first started looking at how we could change the simulation by changing the action that gets passed into the simulator. And so from the standpoint of the policy, it's choosing its actions normally, but after it chooses its action, that action is actually going to be modified in some way, which causes the simulator, functioning as it normally would, to output a new state, which is actually going to be closer to what we would expect to see in the real world. So the way that we do this is we're augmenting our simulation with what we call a grounding module. This grounding module is just an additional function which is added to the simulator between the policy and the environment. The grounding module looks at the current state of the environment and the action the policy is computed, and then outputs a modified action, which causes the simulation to behave more like what we would expect in the real world. So the question then is, okay, well, what is the right grounding module to produce a more realistic simulation? So the first algorithm we introduced along this that was looking at modifying the simulators, the action passed into the simulator, operates in the following way. So once the action is sent into this grounding module, there's first a step of predicting, well, what would happen if the same action was executed on the physical robot? So this is a supervised learning problem because we've already collected some real world data where we have trajectories of state, action, next state, and so on and so on. And from this real world trajectory data, you can compute a supervised learning data set of state, action, where your input features are states and actions, and your output targets, or you're trying to regress to the next state which would arise. So that's a supervised learning problem that can just be solved with, for instance, a neural network is what we used. And then the next step of the grounding module is to choose an action which will cause the same effect in simulation. This can be solved with an additional supervised learning problem where we run a policy in simulation and collect trajectories in simulation. But now the supervised learning problem changes a bit. We want to have as input a current state and a desired next state, and output what is the action which would produce this change in state. So this is known as an inverse dynamics model. So the total composition of this grounding function is to first predict the real world effect using a forward dynamics model, and then using the simulator's inverse dynamics model to compute the modified action, which will produce should produce a more realistic state change in the simulator. So we take this grounding module, augment this interaction loop with it, and this, in principle, is now going to make the distribution of trajectories that the simulated policy sees better approximate the real world distribution of trajectories. You show one example of this. This was some further analysis that we did. By the way, so the work I'm talking about was first published at AAAI in 2017. We just had a kind of more full version of this work that was published in a special issue of ML, the Machine Learning Journal this year. So I'm showing an illustration here of kind of how this is working. So this is a really simple modification. In this task, we're just commanding the robot's left shoulder, one of its left shoulder joints, and we're applying a constant action. We're telling it to move its shoulder joint to a position of -15 degrees in angle. And so what you can see by the red curve here, so first of all, on the x-axis is time. So we're computing a command over time, and the y-axis is the position of the joint. So without grounding the simulator, the joint's very compliant. So we almost instantly kind of achieve the desired position in the simulation. But if you run the same action on the physical environment, that's what's shown by this solid dark blue curve here. It takes much longer for the joint to respond. And in fact, in the 200 time steps, it kind of doesn't get all the way to the target angle. So what the grounded action transformation algorithm does is it instead replaces the action of move to -15 with an action that is actually only more slowly moving the joint in position. You can see it's not perfectly accurate. The resulting grounded state is suboptimal, but it's qualitatively much more qualitatively a similar motion, and kind of quantitatively there's less error between the trajectories of the joint position. So one of the main applications that we did with this was optimizing the walking speed of robots for robot soccer. So on this, I'll show the videos of this. What we did here, we collect 5 minutes of walking data on this now robot, and then we optimize in simulation using reinforcement learning, which involves 5,000 minutes of walking on the simulated robot. So this would be a prohibitive amount of experience to collect on a physical robot. We start with this initial hand-coded walk that I showed earlier. So this hand-coded walk was a walk that was open source released by a different team competing in this international RoboCup competition. At the time, as far as we know, it was like the fastest one available that you could use on the now robot. We then apply reinforcement learning. So here's the grounded simulation. The key thing to point out there is that the robot's walking much more unstably, which is kind of more like what we see in the real world. And so then after we apply reinforcement learning, we end up with this walk, which is we have a couple of iterations of our algorithm. I can go into more details about that offline, but we end up with a walk which is 40% faster, which was the fastest that we know of anyone achieving on this robot. I'm going to show just like a bit more of kind of some of the, what's happening here. This first plot is showing one of the ankle joints of the robot. So you can see that on the simulated robot, the ankle doesn't really move as the robot walks. So this is just like, it's the same policy deployed in simulation and deployed in reality, but the joint just isn't moving at all. Whereas on reality, you can assume, I'm assuming this is because the robot can't hold, as it's walking, it can't keep that joint perfectly fixed. So there's some variation in the angle that the foot moves at. So you can see this more sinusoidal motion. It's a bit difficult to see on this plot, but there's a light blue curve kind of hidden behind the real world state. And so that's from our forward dynamics model predicting what would happen in the real world, given that we were in certain states. And there's also even a bit harder to see on the plot is the grounded action, which is similar to about where the predicted state is. And that's the angle that the grounded action is trying to move it to. And so that will cause the simulator to produce the same, to produce a similar trajectory once it's grounded. There's a slight technical difference between how these two plots were created. I'm not going to go into all of the details of it, but I think this new plot I'm showing is kind of what is actually happening when we're doing reinforcement learning. So we don't quite get the same minimization and error that's shown in the left plot, but we're actually able to kind of add in at least some of this motion, which is seen on the real robot. And so that's gonna, that helps us when we're doing reinforcement learning. We're actually capturing some of what's happening in the real world, whereas the simulator isn't capturing it at all. So that was the grounded action transformation algorithm. This was the kind of the pipeline for modifying the robot's actions in order to achieve a more grounded simulation. Since this original work, we were able to kind of show that this worked really well for one task of optimizing the walk speed of a robot. There's been several advances that I'm going to talk about here for how we've improved this grounding process. So the first thing that I want to talk about is what's called the stochastic grounded action transformation algorithm. And so this is one of the problems that the original algorithm has is that it's assuming both a deterministic real world and a deterministic simulation. The deterministic simulator, that's debatably, the simulator is something that you control. So you can make it deterministic if you want. Just use a deterministic simulator if you can't control it. But the real world, in general, like the effects of the robot's actions aren't a deterministic function. There's things that you can't model, and that leads to a kind of noisy distribution over the next states. So this was work that was led by Sid Desai and Haresh Karnan at UT Austin. And the key insight here is that instead of just predicting a single best next state, we actually want to model the distribution of possible next states that could happen in the real world. And so then instead of just taking the single most likely real world effect, when we ground the action, we're going to put a sampling operation there. We're going to sample from the distribution of possible next states, and then choose the action which causes the sampled state to occur. So this is basically a way of trying to capture some of the noise which happens in the real world, and then reproduce that within the simulator. So one of the cool applications of this work was we're looking at a now robot walking over bumpy carpet. So there's no modeling of like kind of bumpiness in the simulator. And it's not even like it doesn't appear in our data when we record state action, next state trajectories on the robot. And so what this, because there's this unmodeled effect of the bumpiness of the carpet, it just makes the real world much noisier. So this is several shots of the robot walking over the noisy carpet, and it ends up being like, much more unstable. And so if you just try to apply grounded action transformation as we did before, the policies learned tend to fall much more often than they would on smooth carpet. But if you apply this new stochastic grounded action transformation algorithm, because you're modeling the real world noise, you're learning more robust policies to it. So in the quantitative results that were in this IROS paper, we show that while grounded action transformation learns a walk which is a little faster, it ends up falling much more often, whereas stochastic grounded action transformation learns a walk which is robust and doesn't fall, but it still is also faster than the initial walk, as well as what's learned by baseline approaches. I'm going to talk about a couple of more advances. So one other, another approach which also appeared at IROS last year was to realize that you can view this whole grounding process as kind of like a meta reinforcement learning process, where your grounding function is another reinforcement learning agent whose task is to look at the current state and the action that the policy we're learning selected, and output a modified action. So instead of trying to ground the simulator through supervised learning, we instead can train this module end-to-end via reinforcement learning. I'm not going to go into more details. If you're interested, you can feel free to ask me questions, or I can point you to the paper. I'm going to talk a bit more instead about this more recent approach we've been working on called generative adversarial reinforced action transformation. It's a similar idea to the reinforced action transformation, except instead of using reinforcement learning, the key insight is to view the grounding process as trying to get the simulator to imitate the real world. And so this uses an approach called adversarial imitation learning to bring the simulator closer to the real world. If you're familiar with generative adversarial networks or GANs, then you're kind of already familiar with how this approach works. Essentially, we have the real world is going to output some distribution of states and actions and next states. And then the grounded simulator is also producing a different distribution of states, actions, and next states. These tuples of transitions are passed into a discriminator neural network, which attempts to classify between what is a real world transition and what is a simulated transition. And the goal of the grounding function is we're trying to learn a grounding function which can trick the discriminator so that the discriminator can't tell the difference between simulated transitions and real world transitions. And so we see that this was on some simulated domains, basically reinforcement learning benchmarks, which have been modified to resemble the sim to real problem. We show that with much less real world data, Garrett is able to ground the simulator better than the original grounded action transformation algorithm. So namely, you can see that if you just you have a single trajectory of real world data, Garrett is able to ground the simulator with about as much error as if you gave 100 trajectories to the original grounded action transformation algorithm. And of course, if you give Garrett even more data, then it drives the error down even lower. So here's some examples of, so this is all of the evaluations so far with Garrett has been on like simulated domains, which are often used in reinforcement learning as benchmarks. So this is a hopper domain where there's a source environment where the motors have higher friction than a source environment, or sorry, the source environment, the motors have less friction. So this is the target, like kind of real world environment that's created, and the policy just optimized directly in the source fails to transfer. However, once you've modified the target domain, then this is the same policy acting in the target domain. So you can see how because there's this increased friction, it's like moving a lot slower than it was in the source domain, but nevertheless, the policy is able to learn there because it was developed in a simulator that accounted for this. Okay, so this is a quick summary. I want to start to move on because I've got another part of this talk that I want to, a bit more things I want to cover. But this is just kind of the key distinctions between, so we now have a family of algorithms. The kind of initial limitations we had was that we were unable to represent stochastic environments and had these two learnable functions. And there's some technical difficulties with why having two learnable functions can lead to a bit more instability with making the simulator more realistic. But with this newest algorithm, Garrett, we're able to overcome both of those limitations. So I think that's been exciting, although there's still, we have yet to apply Garrett on actual physical robots for sim to real. So I'm moving towards the conclusion of the first part of the talk, and I'm going to change gears a bit. So let me wrap up with some open questions here. First of all, identifying what to modify. In any environment, if you want to apply reinforcement learning, not everything has to be modeled perfectly for reinforcement learning to be successful. So I'm very interested in how we can identify what is important to modify, what are the right levels of abstraction to enable successful policy learning for a specific real world environment. Another interesting question is how we can use abstract simulations. Much of the Sims real literature, including what I've talked about today, is focusing on using high fidelity simulators that try to model as much as you can about the real world. There's inevitably with a high fidelity simulator, there's still a reality gap. So but there's still the Sims real challenge. I'm interested in kind of the question of what happens when we go from high fidelity simulators to actually very low fidelity simulators, where things are just more represented with a more abstract way. I'll give an example of that in a second. And then I'm also very interested in how we can just, instead of putting all of the learning in simulation, can we learn how to learn in the real world so that we can, we'll still do the final policy learning in the real environment, but we want to use the simulator to kind of like improve maybe how the policy explores in the real world, or just other ways to speed up reinforcement learning once it's applied in the real world. As one example of abstract simulations, and this is the subject of an ongoing project here at UW, one example would be like you're trying to learn to play soccer, and you're representing the game of soccer as a bunch of circles moving around on a 2D plane. So, the question is, what can you learn in this very abstract representation, which can then transfer onto, having real robots moving in a 3D environment. So the key takeaways from this part of the talk are that simulations do offer a method to increase the data efficiency of reinforcement learning, but a simulator taken off the shelf isn't going to have good predictions of the effects of a robot's actions. And that's going to hinder reinforcement learning. So to address the Sims real gap, we've introduced a family of algorithms based on transforming the action of a policy before it's passed into the simulator. And we've demonstrated how this can improve data efficiency for reinforcement learning in robotics. So at that point, think there's about 15 minutes left in the slot, but I have a bit more to talk about. So I can pause here and take some questions about this first part, and then I can move on and talk some about the second part. So I guess, are there any questions in the chat right now? I could take one or two before moving on.
So nobody has posted anything yet. I had something, but it's more of a discussion-y kind of thing, so it might be better to just let you go on and
Okay.
save it for the end, unless somebody else has one that's more timely.
Okay.
Yeah,
I'm
let's
fine.
go on and give you a chance to get to the rest of the stuff.
All right, sounds good. Okay. So this first part of the talk was on improving how a robot can predict the effects of its own actions. So in some newer work, we're looking into the question of predicting what other agents will do in an environment. So when your robot, or actually in the subject of this, an autonomous vehicle, has other vehicles around it, it might want to predict what their future behavior is going to be, because that's going to influence how the robot or the vehicle itself should act. So the particular problem that we're looking at is prediction under occlusion for autonomous vehicles. The task in prediction is that our agents in the environment, and it sees a lot of other agents, such as other vehicles driving, and so it has observations of their past behavior, and now it needs to predict what the future trajectory of these vehicles is going to be. So one question might be to ask, for this example scenario here on the bottom right, what is the goal of vehicle number 1 going to be? In this scenario, first of all, this work was done in the UK. So since this is an American audience, note that the vehicles are driving on the left here. So we have the goal of vehicle 1, and we see that vehicle 1 is slowing down as it approaches this junction. So there's 2 reasons that it could be slowing down. It could be slowing down because it wants to allow what we call the ego vehicle, the vehicle that we're controlling, to merge out in front of it, because the other vehicles are stopped at a red light. So sometimes people are nice and let you pull out. The other possible explanation is that there's a oncoming vehicle that can't be seen, but that vehicle number 1 wants to turn right, but it's waiting for vehicle number 4 to come on. However, in the problems that we're interested in this work, was that we actually can't observe vehicle number 4. So it's occluded by this vehicle around the corner. We can't see that there's an oncoming vehicle. And so then to us, it's going to appear more likely that vehicle number 1 is trying to let us merge out in front. And so if you kind of just blindly use this reading, then the ego vehicle might merge in, and then it would have to stop really quick, or maybe back up once it sees that in fact there is another vehicle that's oncoming there. So because we can't observe vehicle number 4, it's difficult to predict what the future behavior of vehicle number 1 is. The other question that we might ask in a scenario like this is, what does the behavior of vehicle number 1 tell us about the region of the scenario that we can't observe? So in this work, this is a kind of the quick summary of it. We're going to show how what we call occluded factors, meaning just unobserved vehicles or pedestrians, can confound the ability of a single agent to recognize what goal other agents are pursuing. We're then going to introduce an algorithm that infers vehicle goals and possible occluded factors, meaning that it recognizes when there might be something that's missed. And then we evaluate this in simulated driving scenarios with occlusion, and show that this type of reasoning results in fewer collisions, as well as more accurate goal recognition. So better prediction of what other agents will do. There's been a number of related works in this space. So goal recognition is a really important problem for predicting what other agents will do. This just means to predict what another agent will do, you first predict what goal it's trying to achieve. So there's a long history of using inverse planning as an approach to this. And in the context of autonomous vehicles, our work is kind of most closely related to this IGB2 framework for prediction and planning, introduced by my co-author, Stefano Albrecht, this year. And And then there's also deep learning based approaches. So you ingest take a ton of data of what vehicles have done in of trajectories of vehicles, and you can predict what they do in the future as just a supervised learning problem. Separately, there's been work on trying to perform occlusion recognition, so detecting occluded factors based on the behavior of other vehicles. So in a sense, these works use the behavior of other agents as like an additional sensor to detect things about your environment that you can't perceive with your primary sensors. However, it turns out there's some difficulties when you try to put together both of these capabilities in the presence of occluded objects. And so one of the key contributions of our work is identifying these difficulties and then introducing an algorithm to address them. So just as a quick background, this was some previous work which appeared at ICRA this year on interpretable goal recognition for prediction and planning, or IGP2. One of the key components of this approach is that you need to infer a probability distributions over the possible goals for vehicle I in a given scenario. And you don't need to understand everything which is happening here. I'm going to just point out kind of the key parts. What happens is that first the algorithm looks at a vehicle that it's trying to predict for, and it computes the optimal plan for that vehicle for a particular goal. And so in the implementation, they used a version of A* for this. And you then look at the reward for actually following that optimal plan, going from the current observation of the vehicle. And then you do a similar computation, but looking from your first observation of that vehicle. So what you can think of as like the initial state of the vehicle you're predicting for. And intuitively, what this is giving is a difference. It's a measure of how irrational the agent's past behavior was with respect to the optimal plan since you first began observing that vehicle. So the larger this difference is, the lower the probability is going to be between, the larger the difference, the lower the probability that the vehicle was actually trying to achieve this goal. One of the key benefits here is interpretability, because it's based on inverse planning. You can explain the final prediction as being optimal with respect to a certain goal. The downside of it is that it assumes that inferring the goal is sufficient for explaining vehicle behavior. And so when there are actually occluded vehicles or occluded pedestrians in the environment, this is not the case. So with occluded factors meaning hidden pedestrians or hidden vehicles that we can't see, or really just any unobserved entity that is influencing a vehicle we can observe. Before introducing our approach, I'm just going to make the following assumptions. We're going to assume there's a finite number of occluded locations, and that for any location, we're going to reason about whether there is an occluded factor there or there's not. So with this scenario as an example, we're assuming that we can detect that there's a blind spot around the corner, and we're going to say either there's an oncoming vehicle there or there's not. We're not going to reason about all the possible many states of what could be behind the corner. So then, given these assumptions, the algorithm we introduce, called goal and occluded factor inference, is a simple advancement upon just originally doing goal recognition with inverse planning. We just now are reasoning over all of the combinations of possible occluded factors as well as possible goals, and we're looking at how irrational is the behavior of the agent under a particular goal and included factor state instantiation. So I know I'm moving a little quick through this, so I'm happy to take kind of questions after if it's not clear. But I think the key things that I'll point out are that so we're maintaining the interpretability as being able to explain inference in terms of what is in terms of optimality with respect to the state we're inferring. And but now, because we're modeling the possibility of occluded factors and scenarios, we can explain behavior based on both goals and occluded factors. So for time's sake, I'm going to skip over this slide. The quick idea is that in order to have better action selection, you actually have to integrate these predictions into some sort of planning algorithm. So we use Monte Carlo tree search. You can think of Monte Carlo tree search as just like a very focused reinforcement learning procedure for finding like the best action to take at the next time step. So we conducted an empirical study in this work trying to answer the following questions of, can GoFi lead to a higher posterior on the true goal and occluded factor state? And does inferring occluded factors actually reduce collisions in scenarios considered? So we have several scenarios, but I'm going to skip to the end. So here's one scenario where we have the ego vehicle is driving behind another vehicle, and we want to predict what is that vehicle going to do. The ego is going to observe that the other vehicle is slowing down as it approaches the junction. If you just reason about goals in this case, the most logical goal to conclude is that the vehicle is slowing down because it's about to turn left. And because it's about to turn left, this doesn't influence the ego at all. So the optimal action for the ego is to just continue at like maximal as the fastest allowable velocity. However, in reality, the vehicle is slowing down because there's a pedestrian crossing in front of its path. And what the ego really needs to do is recognize this possibility, and then it will slow down so that it has time to actually stop if in fact there is a pedestrian crossing. And so we show with our GoFi algorithm, which is kind of showing this joint inference, it detects the presence of the pedestrian and begins slowing down before its sensors actually pick up the pedestrian on them. Whereas if you just run if you're just inferring based on goals, so you can see this vehicle slows down, it believes that the vehicle is going to turn left, and then isn't able to stop in time for the pedestrian even once it's able to detect it. Okay, so I'll gloss over this, but so we do look at like the collision percentage compared to several baseline approaches and show that this type of reasoning is beneficial in scenarios where there's occlusion. So to wrap up this part really quick, we think that this type of framework, one of the big open questions is how we can consider taking more information gathering actions. So if you have some uncertainty about if there's an occluded factor present or not, then you should take actions to collect more information to make that determination. And we think that the probabilities that our algorithm infers give a starting point for this. And then there's also several questions with integrating our framework with perception modules. The key takeaways I want to leave you with here, though, are that, first of all, goal recognition can be confounded by unobserved occluded factors. To me, I think this was one of the key contributions of the work, was just identifying that this problem existed. And then we introduced an algorithm that both jointly infers goals and occluded factors. And we showed the importance of doing this joint inference. And this led to fewer collisions in autonomous driving scenarios. So in conclusion, I've talked about a couple of different directions for accurate prediction for efficient reinforcement learning. I think these two directions are just a subset of all the, the many different ways we can try to extend reinforcement learning to be more applicable to real world problems. So if this is something which is of interest to you, I'm always happy to chat more about it. Finally, I just want to acknowledge my collaborators at the University of Texas, University of Edinburgh, Oxford University, and 5AI. And with that, here are some of the references for papers for what I talked about today. Again, thank you all for having me at the seminar, and I'm happy to hang around, and I'm going right up to the end of the time slot, but I'm happy to stick around and answer any questions now. So thank you all.
Thank the speaker. I think you'll only hear, well, you won't hear the Mike and Bilge clapping because they're muted. And I just realized there's chat and there's Q&A and they're different. So there is one. All right. So there's a question in each, and then I had a question as well. But actually, can I unmute Kevin? Let me see. I am going to allow Kevin to talk and let him ask his question.
Hello, can you hear me?
Yeah. Hi, Kevin.
Oh, hello. Yeah. So my question was about the goal and occluded factor inference sort of problem specification. You set it up. Yeah, you say that the one of the biggest contributions was really identifying and classifying the kinds of problems that would come up when you try to merge those two perspectives. And the approach that you presented there was sort of a fairly constrained set of occlusion options, and you had to sort of put in what could be there, what are the ways it could be occluded, those highly constrained from a really general learning perspective. What do you think is the right way to go forward? Because that doesn't seem all that scalable to me. What do you think is the right way to go forward to sort of move away from that like hard-coded, hand-designed kind of algorithm approach to something that's a little bit more learning-based or flexible?
Yeah, so I think that's a good question. So I think there is some ability to use like something like blind spot detection, or properties of like a static map to actually identify where, make this process automatic, where you can identify like these are regions I can't observe. I need to behave more cautiously with respect to those regions. That being said, so this the general class of problems that we're dealing with is it's an instance of a partially observable MDP. So there's kind of, if you really open yourself up to all the different possibilities, then you always do run into a scaling issue there. So yeah, at this point, I think it's coming up with strategies to identify what are actually realistic sets of where occluded factors could be, and then what are kind of the worst case instantiations of those occluded factors. That was the main line of directions that we've been discussing. So if you can't see around the corner, there's a lot of things which could be behind the corner, but you really want to infer the possibility that it's something which is going to severely influence your actions or be very risky. That's what you want to be inferring. So that was kind of the main line of discussions we'd had there. Does that make sense?
Yeah, it does.
Okay, thanks. So a question from the chat from Nitsan. Actually, I will let him ask it, and then I will probably have a follow on for it. So
okay. Hi, can you hear me?
Yes. Hi.
Great. Yeah. So I'll just read out my question. So based on the first presentation, we saw that the ideal motor angles differ from realistic motor angles, and that the grounded sim you showed is able to improve accuracy because it better models the real motor movement. So I'm wondering for robot actions, are these motor movement discrepancies the main issue that's causing differences between the sim and reality? Or maybe there are other factors that we also need to model, and then that'll make the sim even better. And this is all assuming that the environment is very deterministic. So just looking at the robot actions, the robot hardware.
Yeah, that's a good question. So maybe part of the initial answer would be that we do notice that the motor movement is a discrepancy between simulation and reality. And then, empirically, we realize that we see that correcting that discrepancy leads to better learning. So I think I suggested as, one direction for future work is what do you need to modify to support reinforcement learning? The goal isn't to have a perfect simulator. It's to have a simulator which is sufficient for learning an improved policy for some task. So I don't suspect at all that it's the only part of the reality gap. So I think even in the context of robot walking, there are discrepancies between the friction of the surface the robot's walking on in simulation and reality, but we don't have to do any sort of changes there to promote the success of reinforcement learning there. Yeah, does that answer your question?
Yeah, so you're saying there are other possible factors that cause the reality gap.
Yeah, I mean, I think almost certainly there's probably a lot of other factors. I think what's cool is that we don't necessarily have to correct for all of the other factors. And so, in this case, where we manually identified by looking at trajectories of how the robot moves in simulation and versus reality, we identified one and we focused on correcting that. But you could imagine okay, so you have a discrepancy in motor movement or how you're modeling the floor, or possibly other things. So how do you which of those need to be corrected for reinforcement learning to be successful and transfer across the reality gap?
Thank you very much.
Yeah, thank you.
And then I think you partially answered this, but a follow-on question to that is how possible is it, if you don't necessarily even know what your gaps are, to use this as a way of diagnosing your gaps, and possibly even using reinforcement learning as a way of identifying, if you don't observe the problem, then you can't identify the problem to try and correct it. How can you, how would that fit into this pipeline where you don't necessarily know what your problems are?
Yeah, so I think, one approach would be to kind of, you can see if you can correct it with the approach. And if that fails, then that helps you identify that, okay, well, correcting that isn't sufficient for it. And then, but at the moment, I guess I see that then that still requires some manual digging of what are the other, manual identification of other potential issues. I would have to think more about, could you use the approach to automatically identify where your issues are if you don't already know where they are? Yeah, that's a good question.
Okay, and maybe we'll take one last question, because I think this, again, it's closely related to what we were just talking about. So if I can find Bosun to allow him to talk, I will let Bosun ask this question.
Hello, can you hear me?
Yes, I can. Hi.
Yes, I have first, thank you for your fantastic presentation, and I have
Thank
a question about your first part. I see you put the mitigator in the action generated stage after the policy generation, but I think the gap between the real world and the simulation is about the state. So I'm just wondering why you don't put the mitigator such as a predictor in the state age, that is the state generated from the real world, and then put the such as predict a state then grow into the simulation.
Yeah, it's a good question. And so I think one of the key things is that when we're applying reinforcement learning, the learning agent is going to explore new agents. So we're going to see we're going to go to possibly some regions of the simulator. We're going to see states in simulation that we haven't seen in the real world. And so we don't have any data on what would happen. So we're trying to learn functions which can generalize based on some data, but we can't simply look up what the next state should be. Now, maybe the other, if I understood correctly, maybe another part of your question is why change the action, and why not leave the action alone, let the simulator work as normal, and then a new state comes out, and then we change that next state. And so I think some of the difficulty there is that if we're doing that, then what is the purpose of having the simulator in the loop at all? And that begins to look a bit more like a model-based reinforcement learning approach, where we might try to just learn from real-world data, learn our own simulator that gives the next state. And so there's, I think model-based reinforcement learning is a really exciting area, but there's still a lot of work to do there. And I think part of the motivation of this work is we already have really good simulators. People have invested a lot of time and effort into developing good simulations of robots. So how can we leverage these already provided resources instead of trying to learn things from scratch? So the problem I guess I see with modifying the state after it comes out is then it's throwing away the computation the simulator did, which is what we're trying to leverage in the first place. Does that answer your question?
Yes, exactly. Thank you.
All right, thank you.
Okay, so in the interest of time, I think this is a good place to stop. So let's thank the speaker again. You can, I don't know what the virtual version of applause is, to like clap in the chat or something like that, or thanks again.
Thanks again for having me.
And we will, I guess, reconvene in a month with next month's speaker, which will be the first Friday in November.